Hello, everybody.
Hello, Prof.
How was your weekend?
Fine.
Good, good. So today, rather than cover new material, I thought we'd take a breath and kind of go back over some problems. People had kind of suggested it would be nice to kind of go over some practice problems, etc. So I figured we would do that. You good with that?
Yes, Prof.
Have you guys tried to work out any practice problems on your own?
Yes, sir.
Okay, cool. Well, we'll run through these and see how you do, and then we'll get a better idea as to, if we need to work on it some more or what. Go ahead and share my screen. Now we can get started. There we go. So we'll do practice problems today. And I'm going to start from the basics, and we're going to work to get more complicated as we go. We'll see how much we get through. We're not going to have class on Wednesday. I'm going to be at a conference. And right at our little time is when I'm going to be on a panel. So we won't have class until Friday, and I'll send out that email just so everybody knows when I send out the link to today's video. So here are all the basic relationships that we have so far. And these are probably about almost the only ones we're going to get. I think we'll have the formula for the multi-layered atmosphere will be probably the last formula that we have. But today we'll start with these. Okay, and this one over here, the fourth root of this value here is just a rewriting of the Stefan-Boltzmann relationship. But it's highly useful because if you know the power being radiated from something, then you can determine what temperature it is. Stefan Boltzmann says if you know the temperature, you can figure out the power per unit area, so you can always solve for T, and that's all this thing is here. And each of these three, all of these can be boiled down to this one, right? This is just a different way of writing these two. So really, you don't have all that many. 1, 2, 3, 4, and I'll probably give you a fifth. So hopefully that's not too difficult. You just have to know how and when to use them. That's usually, the first step is figuring out exactly what formulas you're going to need to use a particular problem. So we're going to start out with one. Do you all have a slide or some notes that have these on them? Because if you're taking notes, this would be a good thing to copy. Again, you don't need to copy, I should probably just remove these guys because they're all the same ones, right? Okay. And I think we know this. So these are the things you'd want to copy into your notes. For the Stefan Boltzmann constant, remember it's just 5, 6, 7, and 8 are the numbers in here. So it's 5.67 times 10 to the minus 8. For your Stefan Boltzmann constant, not too hard to remember. I'm fine for the Weems displacement law. If you round this to 3,000, a lot of people do. Often in the ones that I work, I use the normal value, but you could use 3,000, that's fine. Rounding is perfectly okay. So we'll just start with the simple one. The sun shines 1360 watts of energy onto a square meter of an Earth satellite for a half hour. Now this 1360 watts, anybody know what value that is? Why did I pick 1360 watts?
It will be energy.
right? And so this is what we call our solar constant at Earth. Okay, that's a good number to always know. It's 1,360 watts. That's our solar constant. At the place where our Earth is, that's how much energy is kind of raining down onto the Earth. And so I picked a satellite up in space, and I want to know how many joules of energy are transferred to that satellite for a half hour. Yeah. So go ahead and work out that problem. Put out your pencils and a piece of paper. And then when you get an answer, stick it in the chat. Okay. And for those who are watching this video and not doing it live, I want you to still work on it too. And just pause the video until you've worked out your answer, and then you can restart it. So I got one person that's put in their answer. Anybody lost? So which of these are we going to use?
The first one.
Yeah, the power equals energy divided by time. So our power, remember watts is a unit of power. It's joules per second. Okay. Okay, here we go. Let's see. So we're going to use that formula. Energy equals power times time, right? And so we've got 1360 watts. It's the same thing as 1360 joules per second. And then remember, it's times time, but we need a half hour isn't going to be the right units because our watts are in joules per second. So we have to get time in seconds, and a half hour is 1,800 seconds. And so our number should be around there. Shepard, do you see how we're getting that? Shepard,
Yes,
is that
Prof.
Okay, good.
Yes, Prof. Yes, I'm following.
Okay, so now we're going to do a variation of this one. I like for you guys to think about stuff. So say the sun shines its same solar constant onto the Earth. Now the Earth has an albedo, so how many joules of energy are transferred to a square meter on Earth's surface over 1 hour? But now you have to factor in the albedo. Caldrian, how are you doing on your calculation?
I'm not necessarily using the correct equation. I'm trying to plug in the numbers, but I'm thinking.
So does everybody remember Earth's albedo? What's that value?
I use 30%, sir. I don't know if
Yeah,
it is.
yeah.
It is
0.3 is our albedo. And remember, that's the amount that gets reflected, right? And so what we want to calculate is the amount that's getting through past the albedo. So that would be 1 minus the albedo. Okay. So we take our 1360 and multiply it by 1 minus the albedo. So if it's reflecting 30%, then that must mean 70% is getting through. So 70% of 1360 is 952. And again, that's going to be watts per second. And so now we're using the same formula we did before. Energy equals power times time. Only now our power is 952. And we have to use the number of seconds. And this is wrong. This should be 3,600, right? And so if we do that, this number is wrong. 3, 4, 2, 7, 200. Everybody get how I got that? Is that clear? Remember, when you use this albedo, the albedo tells us how much is reflected. And so we always have to
Yes.
do 1 minus the albedo. And an hour should be 3,600, 2,600. So Zach, you were spot on. Thank you. Okay. So we're going to switch gears here now to black body radiation. So if you've got a pot of boiling water, what is the peak wavelength that it's boiling at? And is this visible? So I'm going to go back to your formulas. Got a pot of boiling water. That means you need to know the temperature of boiling water. I assume you all do. If there's anybody who doesn't, speak up now. So which formula are we using?
Peak wavelength.
Yeah, the Wien's displacement formula. And what value are we dividing it by? What temperature should we be dividing it by? For boiling water.
What's it be, Kelvin?
It's got to be in Kelvin. That's really important. So what's the value in Kelvin for boiling water? What's our value in Celsius for boiling water?
100.
Right. And so what do we always add? What's the number we add to Celsius to get Kelvin? That is 273. And so what is the peak wavelength folks are getting? And are we visible? Can we see that?
No, we cannot see that. Let me see.
We cannot. Now, what is the units that we get out of this when we use Wien's displacement law? 2897 divided by the temperature in Kelvin. Remember that those units are always going to be in microns. Okay, which is a millionth, right? And so 7.76 microns, we're not into the visible spectrum until we're much shorter wavelengths than that. This is too long of a wavelength. So as one might expect, when you look at a pot of boiling water, you do not see it glowing. Okay. So what temperature does an object have to be for its peak wavelength to be in the visible range? What temperature does an object have to be for its peak wavelength to be in the visible range? And I'll put this back up here. And then when you get that temperature, paste it in the chat. Okay. Since we're talking about peak wavelength, we'll still have to use the Wien's displacement law. And so the question is, what temperature does an object have to be for you to be able to see it glowing in the visible range? So Caldrian, you're looking for a temperature. You've listed the visible range. You could use that as your visible range. But I'm not asking what's the visible range. I'm asking what temperature it would have to be to glow in the visible range. And so if you got here, visible range, 0.38, you could go up to 0.86, could use 0.7, somewhere in this range would be fine. But you need a temperature, Caldrian. Your temperature's way, way, way too low. Because we've already said if it's, 373, you can't see it glow. Certainly if it's a lot colder than that, if it's 0.38 Kelvin, you're not seeing it glow. Okay, Zach's got a number. Anybody else? Shepard, what you got? Paste it in.
Hello, Prof. Which number are we using? Because it is from range 0.4 to 0.
Well, so first off, which would you use, the
0.7.
lower end or the higher end? When you would first start being able to see it glow, would you be using the lower number or the higher number? So remember, up until now, we've all been stuck in the infrared, right? Everything that has been glowing, it's say 300, 400 degrees Kelvin. We've been getting wavelengths that are much longer than the visible range. As you get warmer and hotter, the wavelengths become smaller and smaller. So you'd start getting into the visible range coming from the right side here, because you're going to shorter and shorter wavelengths as it gets hotter. So something glowing red hot is not as hot as something glowing blue hot, right? So you'd want to use a value that's on this end of the range. And so you'd still use our Wien's displacement law, but let's just say let's just use 0.7. You could have used 0.8, that would have been fine, but let's just use for this 0.6, okay, or 0.7. So we just use that in Wien's displacement law, right? So switch that around, solve for x. X is going to have to equal, so if the wavelength is 0.7, that's here, equals 2897 divided by t. Okay, this actually should be t, right? And then when you do the math, you're going to get around 4,000 Kelvin. If you use 0.7, it's 4138. If you used a little bit higher, like 0.8, you're going to be slightly lower in temperature. Remember, the shorter the wavelength, the hotter the temperature. Hotter temperatures give you smaller and smaller wavelengths. Since these are all in microns, you'll be getting like 0.6, 0.5 as you get hotter, and then 0.4, and then 0.3 if you get really, really, really hot. Does everybody get this? Caldron, do you see where you went wrong? How did you get 600 to 860 degrees?
Just from looking at the spectrum in nanometers.
Right, and so you see why that doesn't work? So this is just telling you the wavelength, right? It's not telling you anything about temperature. The only thing that tells you about that relates temperature and wavelength is this Wien's displacement law. And so if you know the wavelength that you want to find out, then you can calculate the temperature. Just like if you know the temperature, then you can calculate the wavelength. So you can be given either one of these, and it's just this 2897 is just like a constant that helps you relate the peak wavelength to the temperature. But always remember that your answer for the wavelength is going to be in microns. And so you kind of need to know where your visible range is for that. And so, if you wanted to use 0.86 as the end of the visible range, that's fine. But then that 0.86 is what you would put in for the wavelength, right? So you'd have 0.86 equals this divided by t. So you can multiply both sides by t, divide by the 2897. And then that will give you your, let's see, over here. So 2897 divided by temperature equals 0.7 microns. Rearrange that and you get that value. We all good on this one? So I can give you either a wavelength and you can tell me the temperature, or I can tell you the temperature and you give me a peak wavelength. Now we want to look at power. So we've got the Stefan-Boltzmann relationship here. Calculate the energy being radiated by a 500K black body. So we're going back to these formulas here. Here's the Stefan-Boltzmann formula, and this is your constant. That's sigma is 5.67 times 10 to the minus 8. What y'all getting from that? So for a 500, the temperature is equal to 500. So on your calculator, what's 500 to the fourth? So it's 500 times 500 times 500 times 500, right? That gives you a really, really, really big number, but then you get to multiply it by sigma. And remember, sigma, the Stefan-Boltzmann constant, is a number times 10 to the minus 8. So that big number that you just got is going to go down by 8 decimal points, right? And so you should be getting somewhere in the neighborhood of 354. And what are our units? Our units are going to be watts per square meter, right? Because in our Stefan-Boltzmann constant, you can see we've got watts per square meter per Kelvin to the fourth. But this Kelvin to the fourth is, in the denominator. And so the temperature that you figure out is going to be Kelvin to the fourth. And so the 2 Kelvin to the fourths will cancel each other out, and you'll still be left with watts per meter square. Yeah, Keldrin, that looks good. So anybody have a question about this one? Okay. So Let's see our next one. Let's see which one we want to do here. Do you want to do one of those climate models, like with an atmosphere? Okay. Why don't we do a climate model with a one-layer atmosphere? And in this case, we're going to pick a planet that has an albedo. Let's go with, let's see, Mercury has doesn't have an atmosphere. Or no, we're doing one atmosphere. Well, let's go ahead and use Mercury's albedo, which is 9936. That's not the albedo, I'm sorry, the solar constant. So we're going to go with 9936 is our solar constant, and our albedo is going to be 0.1. Let me go ahead. Let's flip over. So let me point this out. This is one formula I didn't have on our little list, but this is a really good one to have. The energy in per unit area is equal to the solar constant times 1 minus the albedo divided by 4. This was calculated for the Earth here using a solar constant of 1360 and an albedo of 0.3. In our case right now, we have a solar constant of 9936 and an albedo of 0.1. So first you want to figure out what is the energy in coming into the surface. So you've got to use this formula here. What's the energy coming into the surface? So jot down your little formula here. Grab this whole thing. Not gonna let me. Oh, okay. So we got this formula here. You want to plug those numbers into that formula, and that's going to give you the energy in per unit square area, per meter squared. What's nice about this is you don't need to know the diameter of the planet or the radius of the planet. All you need to know is the solar constant and then what percentage of the light is reflected. And that can tell you the energy in. So what do we get for an energy in? It's just 0.7 times 9936. And then you divide that by 4. So what are folks getting? It should be something on the order of 1738 watts per meter square. Everybody agree with me? Okay. How did I get this? Remember, oh, I'm wrong. I'm sorry. I am wrong. because our S in this case is 9936, right? 1 minus our albedo is 0.9. I was using 0.7, right? So 9936 times 0.9 is 8942 divided by, entire thing is divided by 4. So Shepard, you were correct, 2235. So that's a lot of power coming in. Okay. So now you know the energy in. Remember, we're doing a 1-layer atmosphere, and our ultimate goal is going to be to calculate the temperature that the planet is, the surface temperature. Now, do you want me to walk you through this, or you want to do the whole thing on paper and then come at me at the end? It's up to you. Remember, when you start with this, start by drawing, whenever you do these climate models, start by drawing out all your fluxes. So on your piece of paper, you want the sun, want to draw out your surface, and then put in 1 layer for your atmosphere, because we're doing a 1-layer atmosphere. Now help me here, what fluxes should I draw? From where to where?
Flux from the sun directly to the surface.
Okay, good. And then from where to where?
From the surface to the atmosphere, and
Right.
then one from the atmosphere in both directions.
Right, because when the atmosphere absorbs, now because remember the light coming up from the surface, we're now in infrared, right? I mean, and since we're in infrared, that means if we have an atmosphere that's going to absorb in the infrared, that's our assumption, then when it radiates out, it will radiate in both directions. So we got like that, okay. So now 2235, where do I put that first number?
It will be coming from the sun.
So this should be 2235. All right, we don't need all this stuff. Let's. There we go. So we got 2235 coming in. So if 2235 is coming out, what number do I put where next?
Or for 4,471 in the second flux, coming from the surface.
Okay. You are correct, but we haven't gotten there yet. So I want you to do it step by step, because in order to figure out why that number should be doubled. You're right, it is doubled, but why is it doubled? Remember, energy in has to equal energy out to space, right? Energy out to space has to be equal to this. So where does this number go next?
In the in both the arrows from the atmosphere.
Right. So this number is going out into space, and since it's going out into space, it also has to go, it's equal in both directions. So if we apply our energy constraint, or energy in equals energy out, energy into the planetary system equals energy out to the planetary system, that means that the outer layer of the atmosphere has to be radiating as much energy as the energy coming in from the sun. Otherwise, if it didn't, the planet would continue to heat up, and we haven't found its its stable maximum. We haven't found its equilibrium. Energy in equals energy out when you're at equilibrium. And so we're figuring out the equilibrium temperature, the temperature at which the planet will stop getting additionally warmer or additionally cooler, right? And so now this is where your bigger number came from. Since you've got 235 into the ground here, 235 into the ground here, that means since energy into the ground has to equal energy out of the ground, we're now going to be at double this number. So that would be 4470. Everybody follow along with that?
Hello, Prof. I'm lost. I want to understand why you are
Okay.
you are Can you come again?
Okay, let me do it again. Let's see. So let's get rid of all these numbers yet. Let's get rid of all these arrows. Okay. Are you fine with this part? Are you on board with this part? Okay. So we got this amount of energy coming into the planetary system. Okay. Our constraint on doing the climate modeling is energy in has to equal energy out. Okay. If we're getting more energy in than we're putting out, then we're going to start heating up, right? It was like when we took the turkey out of the freezer, there was more energy coming in from the surroundings because it was colder. And so it warmed up, right? Because there's more energy coming in. And it keeps warming until the amount of energy that it's emitting is equal to the amount of energy that's coming in, right? Because if the amount of energy that it was emitting got larger, then it would start cooling down because it's emitting more than it's taking in. And so it's losing energy. So there's going to be some point where it's going to get to the point where the amount of energy that's going away is the same as the amount coming in. And then that's the stable equilibrium, and that's where the temperature stops changing. We're trying to figure out the final surface temperature, so we got to figure out where this energy is going. Sorry. Back here. I need one of these. Okay. So if the energy into the system is this, it's coming from the sun and it passes right through this atmosphere because the atmosphere is transparent to light in the visible range, right? It's transparent to light in the visible range. But we know that if we want to figure out the stable temperature, the amount of energy coming into the planet has to equal the amount of energy going out into space. And so that's that line there. And so that means that this number and that number has to be equal. Otherwise, the temperature would keep changing. Are you good on that? Okay.
Yeah.
Now, the reason why this atmosphere is shooting out energy is because it's hot. Something warmed it up, right? And so when it starts radiating energy, it has to radiate in two different directions. It can't just radiate out into space. It's got to be equal in both directions. So it radiates out into space, but it also radiates down into the ground. It will keep warming up until the amount of energy it's radiating out towards space is equal towards what it's coming into the planet, because that's energy out and energy in. So if 2235 is going out into space, 2235 has to also be coming in. Follow that? Because it's got to be equal in both directions. And so now when we want to figure out how much energy is actually coming out of the surface, we have to look at how much is going in, because the energy going out has to equal the energy going in. We got 2235 coming in over here, and 2235 coming in here. Add those together is the amount coming in. That's 4470. And so that must mean the amount going out is 4470. And what you'll notice, is these numbers work out because that means 4470 is going into the atmosphere. So 4470 has to come out of the atmosphere. Half of it's going into space, half of it's coming to the planet. So now all these numbers equal out. And so now that tells us that the amount of the power coming that's being radiated off the surface is this 4470 watts per meter square. And if we go back to our formulas, all the way up here, if we know how many watts are being emanated per area, then we can figure out the temperature. It's the fourth root of the power divided by the area divided by the Stefan Boltzmann constant, and that gives us the temperature. So let me find where we are over here. So are we back over? Where did my numbers go? Sorry, I'm just trying to find where. Okay, here we go. So we can plug this number into that, divide it by the Stefan Boltzmann constant, and then take the fourth root of that. Remember, when you divide by the Stefan Boltzmann constant, Stefan Boltzmann is 10 to the minus 8, right? 5.67 times 10 to the minus 8. So you're going to be dividing by a really tiny number. So you'll have a really big number, but then you're taking the fourth root of that, the square root and the square root again. That'll give you a pretty warm number. And that's how you would calculate our surface temperature. And if you don't have a calculator that calculates fourth roots, you can, if you just do a search on Google, you can find a calculator that will. Just say you want to take the fourth root of something, and it'll find it for you. Or take the square root of it twice. Does that make sense? Okay, so we got through a one-layer atmosphere. We used a different albedo and a different solar constant, right? Remember, I'm going to put this formula on our formula page. I'm going to upload this problem PowerPoint up to Moodle. So this works for any planet. You might have a different albedo or a different solar constant, right? And in climate change, our albedo may change as we get more melting ice and stuff like that. It'll start to get less, so more power is going to get through, depending.
I have another one after this. Let me check. Thank you very much.
Okay, are we good? Do we need to do more practice? Do you like doing practice? Do you like doing practice where we work it out like this, or do you want just like a worksheet and do problems?
I think both are actually beneficial.
Okay, there are some problems in the back of the book. You all have the book, right? Okay, why don't we start working on some of those, and then I can go over them during class. You know, and try a bunch of different ones. Whatever gives you a stumbling block, we'll focus on that. Because I want you to, I mean, a large part of the rest of the course is not going to be doing these basic power relationships, but I want you to know how to do it. So you understand, you know, why we've got the temperatures we do. And later on, what will make an effect is when we're looking at, well, what happens when we put more carbon in the atmosphere, more carbon dioxide? How does that change our numbers? Okay, everybody, have a great day, and I will talk to you soon. Remember, we won't have class on Wednesday.
Yes, sir.
Okay, thanks.
Thank you, Prof. Thank you.